In today's lecture, it's about actually understanding representation language. That is all it is. Relational calculus and algebra both are SQL languages of representing queries. So the important thing is I will introduce you to the various concepts, but the most important thing that you can do to actually come up to speed quicker is after this lecture and before the recitation, please go over the lecture, the chapter before the recitation, because I'll ask Dimitri to just do a mapping of, take a SQL query, write it in relational algebra, then write it in relational calculus, because that is all you need to understand. You don't have to learn again how to write select statements in SQL. You want to understand how the same select SQL is actually represented and why is it done. How does the optimizer, which I'll tell you in the database, what it does to us when you write that select statement in text, it goes in and converts into relational algebra, then tries to look if it can rewrite the same relation in a different form, and then following certain rules it will choose, thinking that this is the best way to do it performance wise. So this is all the internal stuff that goes in. So relational algebra and okay, the difference between these two, is that this tells you how to evaluate a query. It gives you the relationships as well as how you will do it. So it is called procedural, because it tells you the procedure of evaluation also. While in relational calculus, it tells you only what you want to get. So it is called declarative. So you will see when we will be writing some expressions, I'll take an example and I'll show you guys how to do it. But you will see that this relational algebra tells you, when you write it, you actually tell it the sequence of operations you want it to carry. So what that means is that you can write the same expression in multiple ways. Okay? So all these queries so it takes a relation. So input is a relation. So the input is a relation and output is also a relation. Okay, so if that is the case, that means you can nest them, because an output of one query can actually be fed as input to another one. Okay, so that is very powerful, because then you can write complex queries. Okay, that is a very, very powerful feature of relational algebra. So for example, actually I should go I'll do all the different operations that are there. So let us look at the representation of a select command. Select is represented by sigma, okay, and you are going to give it a relation here, and this is, say, a table which has employees. So E1 is our, say, employees table. So you can say select name from E1. Okay? So what you're doing is, so I'll write a generic statement is, actually because you're doing a select, why don't I break it and do a more generic one? So let us put it as a constraint here. Constraint on a relation. Okay?
I'm sorry, could you just back up a second
Mm-hmm.
and tell me what the purpose of this is? I mean,
Yeah,
we all
okay.
know
Okay.
what purpose SQL queries have because we've used them. But
Okay. So when you write the SQL query, how does the database know what to do? How to decide what sequence, suppose you join 4 different tables. It has to decide that while doing these sequence of steps, which way I should follow, right? So after it looks at your query, when you say select star from, so you wrote this query, okay? So now this will be converted into relational algebra expression inside.
oh,
Okay?
so this is
After,
somehow
yeah, exactly.
languages are designed to do.
No, actually SQL evolved out of these. So that is why internally this is what is doing our job, these mathematical expressions. But because it is easier to write in a, I should say, a language which you speak. You know, it is like selecting. It's very almost, I don't know what would be an English word for it. In Hindi, I can say what it means. Yeah, you can. Okay. Intuitive, I should say. It's something that is you are very comfortable expressing. So that is what SQL gave us, SQL gave us that interface on top of. Good night. Okay. So this is so is that okay? Let me just expand a little bit on your question that you're saying.
Okay, so that's a representation at a somewhat
Lower level.
Lower level.
Exactly.
And so the point of us knowing about it, I mean, do people who design databases need to choose between different representations on that level?
Okay, so you have to understand the most important thing in relational calculus or algebra is one is you can think of just being somebody who writes queries. The other one is who can understand how these get executed so you can write intelligent queries.
Okay.
So this will give you a much more in-depth understanding of the thing. And the other very important lesson I really want everybody to take home with this is that whatever representation is given to you, you can translate into other parts. Okay? It'll make you much more confident also. When you are actually doing something, you'll be able to talk to people who are pure mathematicians and telling them, bridging the gap, basically. Okay?
Ravi?
Yeah.
I know you'll get into it, but the book confused me about project with pi and select with sigma, and so there's unfortunate confusion between select and selection, but that's the way it is.
Oh. Okay.
But I'm new to this, but it seemed to me that this would be a pi kind of a projection, and then the where is the sigma.
Where?
The where clause inside of a select. When we say select, the word select in a SQL query, I might have misread it, but that would use the pi symbol, the Greek pi, for project, and that when you get down to the where clause in a selection, that's what would in calculus be called, or in algebra.
Okay, I'll explain to you why that is the case. Okay? You see this. Okay? This is the constraint. Right? You are putting a constraint here. That's why, because the way I wrote it, I didn't have enough space to write the complete constraint here. Because I just wrote the name and I had to write equal to something. Mm-hmm. Right? So what you're doing is when you do this, I should remove right now because this was in reference to something else. So his question was that when it says sigma here, it is actually mapping to the where clause in our query, right?
That's what
Right? So because here is where the constraint comes. Right? If let us break our query, select name from E1 where constraint. Okay? So this is our generic query. Now what we are doing is, this is where we are selecting a subset of this with this constraint. Okay? So I'll write the pi also here so that you guys can understand what we are talking about. Okay, let me write a constraint here. EID equal to 10. Okay, employee ID equal to 10. Select name where employee ID equal to 10. So this will take the shape EID equal to 10, and this will, so what this did was it projected, so this is now projection. So this symbol, what you did was, here you did not do any constraint here, you will actually get all the names here. Okay, you just projected one column out of this, so you selected a subset of these fields. Okay, while in this you actually constrained it with your where clause. Is that clear now, your question? Is that fine?
So sigma
You were also
returns a subset of rows.
I'm sorry?
So sigma returns a subset of rows and pi returns a subset of columns.
Exactly. So it is working, one is working on rows, one is working on columns. That is exactly the way to summarize it.
You write them with one sentence?
That is the next part. So now, because this is returning a relation, the way we started, that means we can nest these two. Right? Now to write that query, what we want is, we want to select that name. So we will come here and we will say, okay, give me this. Okay? So that is where you have now, is this okay? Is this clear? Okay. Because I want to spend some time here so you guys can actually read through faster through the chapter before the recitation and give Dimitri a hard time. Okay. So that's good. Okay. Next. So here in the constraint, you can have all the operators. Okay? You can have all the operators in there. Okay. The other classification is type of operators. So what we saw was select was working on one relation. So it is called a unary operator.
Mathematicians never objected to calling relationships operators.
No.
Why is this a relation? Why would you think this is actually no? Why do you think this is a relationship?
Like the greater than or less than is a relationship between.
Oh, that okay. So 2 equal to 2 has a relationship.
Right. And first order logic, that's where that language.
It's a Boolean value binary operator.
Okay.
Maps it into one or nothing. That makes sense. Yeah, that makes sense. Look at it that way.
Fine. Thank you, Dimitri. Okay. So if we have a Cartesian product, represented by cross, this would be then a binary, because it will work on, say, A cross B. Okay? So this is another way to describe them, as another attribute, I should say, of operator is what type of operator they are. Okay. So pi would be a unary also again. Okay, let us look at now. Let us make two tables with A1. I don't know how to actually represent this. I don't want to put names. Say N1, N2, name, phone address. Okay, and another table which also has name, and 3, and then this may have, what should I can't even think of. Help me. What are the attributes of a person? Height. Weight. Nationality. Okay, that's good. So H1, H2. Okay. So what we are getting into is how actually to think about joins. Okay, because that is a very important aspect that makes you actually write complex queries. So a join is essentially a Cartesian. So Cartesian product would be, I'll just write, how many do we have? 3, 4, 7, 1. What happened?
Just being stupid.
Huh? I wish we had I had made these tables in the handout, but as it may. So what we are going to see is when we do a Cartesian product, this will go in with this, with this, with this, then this will go in with all these three. So you get a total Cartesian product here. What you should notice is this, because two fields with the same name. Okay, so that's why they can't have the same name, so they won't be named. That is the problem. Okay, so what we have to do is, so then we define, so this is now a Cartesian product now. So then joins were defined. Is it okay? Yeah. Okay. A join is a Cartesian product which is followed by a selection or a projection. Okay, depending on what type of join it is, it will be followed by it. So if we think of, we can actually say, let me give you an example, which is equijoin. So equijoin is something in which, so this is our constraint here. Okay, so we will say this is A, this is B. We are going to say A cross B. And here, what we are going to say is this is the constraint that will qualify this join to be an equijoin. And this constraint we can say where A dot name equal to B dot name. Okay, so now, yeah.
So the generalization would be where there's a constraint of some common element? Or
Exactly. So whatever common element you will give it as constraint, then what it will do is it will take only the first one. From the first one, it won't have this. Because now it knows that they are going to be equal.
So the C is the notation for equijoin.
No, sorry. This whole is the notation of equijoin when C is this. So I meant to say here. Yeah.
Isn't it true that the Cartesian product is going to have 6 rows in this case, whereas your join is only going to have 3 rows?
Normal join?
A natural join.
Natural join. That is the next one. This is equijoin.
So,
Actually, no.
But then
In this case also, yes. This equijoin is going to constrain. This will have only 3 once we have equijoin.
because I don't think you made it clear that you have 6 rows in your Cartesian product, that your join
Would have only 3.
drops it down to 3 rows.
3.
So I just wanted to point that out.
Okay. Let me just finish this, then I'll come to it. Yeah. That is something I missed out. I should have said it along with when I said that this won't be there. Okay. So the second point that happens when you have equijoin or natural join these are not same. Okay? But I want to say it because you brought it up, so I want to clarify this right now. Okay? An equijoin, whatever you will specify here will get dropped out. Okay? If you do not specify a constraint, so what we are seeing is we are seeing 3 representations. One was this, which was Cartesian product. Okay? One was this, in which we have join with this constraint. And then we have another join, which is this. You drop out the constraint, and this becomes, I think it is natural or not natural, right? Not normal, natural join. So what this has is, it has 2 effects, and this also has 2 effects. It is not going to have identical rows coming down. Okay? This will actually have all possible combinations. This will eliminate common rows also. Okay? While this will eliminate, and it will eliminate the columns corresponding to this constraint. Okay? Like we did here, in which we specified the constraint. And if, let me do one more thing, just to clarify this last one. Let us add here H also, okay? So now, when we do this, it is going to drop out this also. Okay? But if we did this with only one constraint, it won't drop out that one.
Is that the same in table B?
Which one? Yeah, both are the same.
Okay.
Yeah, I wanted to make it same so that we know that this extra column will come in, and that is the difference between the two.
But if they're not the same,
Then it is fine.
we just do it, well, if they're both columns titled H, but they have different data in them, do we?
No, the rows won't get dropped. You cannot have same name with, see, what you're saying is that it'll have the same N1 and different H. That won't happen, right?
So
What?
my question is, do you lose a column of data because the names are the same, or?
No, the values will also be the same, right? You have to think.
Not necessarily.
Why? This won't become H3 if it is H1 here.
Right, but
Because it is the same person.
sure, but that doesn't have to be the case. I mean, maybe you both have columns titled H, but in one column or in one table you've measured it differently or something like that or whatever.
So then title would change. Okay,
So okay.
the title, because it would be either centimeters or whatever you measure it in.
Okay. So you,
I mean, if it is consistent representation, then it should be same. It's like giving the same social security number different on the other places. That's all. Yeah.
You have that N3 row in B and not in A. So will N3 appear in the equijoin or the natural join or both?
It'll appear in both.
It'll be in both?
Yeah.
Okay, even though it doesn't have a name.
No, because Cartesian product will take this row and then this row and this row and this. So that is how these rows will
Right.
keep on forming.
But then when you have your constraint of the names being equal,
it's going to throw that away.
Oh, yes, you're right. You're right. Then it is going to throw it away.
it'll
Yes,
throw it
you're
away in the equijoin, but not in the natural join, right? The natural join will keep it with like. some-
Just a second. I'm confused. Whatever is redundant will go away. Yes, it'll get thrown away here. It'll stay here. Okay.
So the natural join just gets rid of duplicate columns?
All the duplicate columns without you specifying them. Actually, I saw one thing. Does anybody have a book? I want to actually, maybe I read it wrong. I was seeing, can I see your book? I saw somewhere, oh, okay. What page number is the chapter at?
It's around page 90, 91.
I thought I saw some 90, 91, some mistake. I thought maybe it was. Yeah, it is in equijoin. If you guys look at it, I don't know if I am reading it wrong or look at the equijoin last statement. What the query is written as is S1 R dot SID equal to S dot SID and R1. Right? I think it should be this. Because it was confusing. If you read the text just above it, I spent so much time trying. I thought that I just totally missed the point of representation. But just is that if anybody else also reads through this paragraph, just see if that is what it should be. Then we can send him an email.
What page was that?
Oh, I have forgot. Equijoin.
If you look at figure 412, he has it correctly done. But here he's got it kind of.
Ah, okay. So it is mistake here and here.
Yeah,
Okay.
It's like a
So,
labeling problem.
sorry. Okay. So just don't get confused because what is happening, just the paragraph above it, he first starts off talking about R and S and then suddenly converts back to R1 and S1. And in the query, then at one place he uses R1 and at one place he uses R. So that whole paragraph actually becomes a little confusing. So just when you just read through it, just be careful. Okay. Okay, the other thing that you guys should realize about all these set operations are what kind of schema is being retained. So like in cross we saw that schema was retained. So when we had R cross S, so the resultant schema does not maintain any of the two. Okay, it actually has a combination of both of them. But there are other operations like So I should actually tell you guys about union compatibility. Okay. So if you want to have other operations like R union S, okay, or R intersection S. So what you are doing is you are actually checking what all exists in this and what is you're comparing it. So you have to have the same schema as well as the column names for both. Otherwise you can't do it. So that is what is called union compatibility. So these two both should be compatible so that you can do these operations on them. Okay? So these, when you'll go through the example, you'll see in the book. This is something just to keep in mind when you are, because then the resultant schema will also be of the one that you pick up initially. Okay? What shall we look at? Okay, so we can, one is I don't know, Dimitri, I was thinking we should, in their recitation today, let's give them examples of just the queries to be written in different forms. Discuss those. Is that okay? Because I think that is the whole idea. Representation is the whole idea of relational calculus or algebra. If we could, we can preferably we'll pick up from the. I'll try to be here also. We'll pick up some from the book itself. So then when they read, it is much more faster. Okay. So we'll pick up some queries. That's why I don't want to go into that right now, but I'll. So let me just give you an example for the optimizer, how the optimizer will work. So so I picked up this query from the book itself. This is from the book. So the schema is also in the book for this. Reservations or reserves. Yeah. So what is going to happen is that when this query, say you wrote a regular SQL query and it got translated to this, when it hits in the database, when it has to now start thinking about how to optimize this query, what is the best way to do it is going to start looking and start calculating temporary relations. So this will make it to calculate something. So it gets the relation back. Then it will go in and do this operation. Okay? And then it is going to go and do this operation. But when the query is translated into this representation, that is when the optimizer is going to look at. So what you are seeing is there are temporary tuples being generated, right? Okay, and you could select before or you could do cross select later on. You can actually do all these changes because everything takes a relation and returns a relation. Okay, so now what optimizer is going to do is it will try to see that all these tuples that are being generated on the way, the temporary relation sets that are being generated, which way it gets the minimum number of tuples returned at the beginning, so that the rest of the operations that are followed on it have less overhead. Okay, so this is how, so that is coming back to your question that you were asking. So understanding that is what it is. Okay, so somewhere there is a parser sitting there. It parsed your query that you wrote, did the validation, then went in and did this.
That's done automatically in the database.
Yeah.
And you can help it by phrasing the thing certain ways, or?
It could be. I think complex queries, yes, you can, because basically translator is not going to do any brain work. You can actually point him to a better query to start off with. Okay. Yeah.
The parser will give you that, but the optimizer might change the order that it does the double.
Right. If it can figure out how actually, how to represent the same relationship or same formula in a different,
size.
or different steps. It may want to do this first and then go back here.
Okay.
You know, it may change the sequence because they can work together.
Okay, as long as it doesn't change result.
Yeah.
It might figure out that certain columns are irrelevant and toss them out.
Yeah. It may do a projection first and get to your, because it knows that all you need is 2 columns out of these 30 columns. Okay? Now let's actually look at how to represent. So this was relational algebra. Okay? You represented everything. You told it what to do to get to this result. Okay? You just didn't specify what the relationship was. In relational calculus, all you do is tell it. So I'll write the same query again in relational calculus. It's this one.
Can you send these statements directly to the database? These relational calculus?
I don't know if there is an interface for this. I know I think it is in what they did with I think it is with Visual Basic they have tried. So there is relational calculus that we are getting into right now. So there are 2 types. One is tuple relational calculus and one is domain relational calculus. So in tuple relational calculus, tuples like these whole rows are your variables. And in domain relational calculus, each attribute is your variable. Okay, so in this, the queries become much more detailed because you have to, if you want to select four columns out of this whole row, you'll have to list all of them. While here, you get returned this whole row. So this is very powerful. This is good when you are doing a lot of GUI kind of work where your queries are simple. And I think Visual Basic, I read it, either it was this book or some other book that where it mentioned that part of domain relational calculus was implemented by Visual Basic and stuff like that. Okay, so that was your question, right? Okay, so let us look at tuple relational calculus, and in this also, let me write the query. That is the best thing to do. That is basically representation. So here are other constraints that you can keep on adding. Okay, so what you want to understand here is that this is our tuple variable. Okay, so one is you should actually, when you are reading the book, try to actually emphasize how to read a query. Really, how actually this relationship, how would it be read? So it is like a tuple P exists in relationship in S. So this is a relationship in Sailors. A tuple P exists where S and Sailors are in reserves. This is now, this one exists. Okay, and in reserves with these constraints. Okay, because this is a tuple, that is why you are doing this. P.sname. Okay, because you are getting this whole row with all the different attributes in it. Okay?
So what's the relationship between, I mean, I can see it as in how you've declared it, but what's the P, S, and R? I don't see how quite.
Yeah, so that is because we don't have the tables in front of us. If I can show, so basically what we have is, say, these are the sailors Who can? So there are three. If we look at the book, we'll do that in recitation, this in detail.
S and R are tuples.
Yeah. No, S is a tuple that is of a relation. So there is a Saylor's table here. So this is going to be an S.
I see. We're just connected through the
Exactly. So just same query being represented in this form. But the main difference that I want you to understand and actually see it directly is it does not tell you how to do it. All it says, this is what you want to do. Okay, in relational algebra, we told it join these tables, do this selection, project this.
Is that PS name supposed to be RS name, or is that PS name?
Sorry, P dot S name.
No, but why is it P and not R? I don't understand.
Okay, because it is in depending on what table it is in, right? Okay, so if you look at these schemas, you will see that the name appears in. So what we are selecting here is the name of the sailor that booked some kind of a boat. Okay, so we want to tell it that when we are doing the joins, we want to make sure that the name of the sailor that is in our result tuple is actually the name of the guy who reserved it. So this is now reserved. So we are actually constraining it here. See, we'll go through this more in detail. I think if we don't have the network connection before the recitation, let's make the photocopies of these tables, and then we will discuss them so we can actually see the query side by side of the tables. It'll just make it much more comprehensible. Okay, so this is the essence of relational calculus and relational algebra. Okay, so what you should do is try to go through the chapter. Okay, we can pick up already maybe 5 or 6 queries that you should look at. I can do that once we are done. So you can actually go through them and we'll discuss those so we can understand the representation part of it, because that would be a big part of your assignment for the projects in the first week. You'll have to write your queries in these two representations.
How does the ER diagram fit into all this?
Okay.
Is that just initial step to develop the table?
So that is where you are conceptually materializing your ideas. Okay, this comes after you have done that, right? Because first you are actually defining their relationships, and then you will go in, because then you will know what tables will be existing. Then you will go in and do these things.
Are we going to discuss those or just pick it up?
No. I'm going to devote one. Did I write in our curriculum that there should be a lecture on ERDs? There is, because I mean that is what we should learn in a database course, and certainly we can learn it on our own. If you guys don't want it, it's fine.
No.
We